Hello, everybody. We welcome you to our tutorial for the IMS 2024 in Washington, D.C. We will have there a Future Directions Day fully devoted to wireless power technologies. And today we just want to give you a short heads up of what you can expect from IMS this year in Washington, D.C. First, we'll have Nuno Borges Carvalho. He is professor at the University of Aveiro in Portugal, and he will speak about far-field wireless power transmission and what events will be devoted to this topic at IMS.
Thank you very much, Jasmine, and it's really a pleasure to be here with you all today. And I'll start sharing my screen where we actually talk about long-range wireless power transmission and its impact on current world. As Jasmine has said, we will briefly express what is going to happen at IMS, and these talks and these activities are part of the Future Directions Committee from IEEE, and especially from the IEEE Wireless Power Transfer Initiative. So let me start briefly by presenting you the problem which we are trying to resolve with some of these concepts of far-field wireless power transmission. And before we start that, I normally like to show you these images of how we are producing world energy, how we are actually building the needs for and the answer for an increasing amount of energy needs, as you can see in these graphs that recently we have been foreseeing in all our activities. And what you can see here is most of the energy being produced continues to be the traditional way, and the clean energies are mainly a small part of this concept. And the problem is that if you produce energy with gas, oil, and coal, this is limited energy. So at a certain point, we'll have a problem because we need to get more energy from the world somehow. And if you see where we are spending energy, actually the countries that are spending more energy, are consuming more energy, are the countries that have more industry. So they are the more advanced countries in terms of industry. And of course, you can see United States, China, and some countries in Europe, Brazil, and Australia, and so on and so on. So this is really one problem of how can we tackle this energy. More important, how can we tackle this need for energy is really where is the energy needs? That is, where can I get energy to my house? Where is the availability of energy? And if you see here in this graph, you see that in most of the world, you can already have access to energy, but there are still problems, well, in Africa and some Asian countries, where it's very hard to get access to electricity. So if you want to have electricity at your home, it's quite hard to get it. And this is not only on these countries. If you look to this graph on the right side, you see that even in Europe, Middle East, North Africa, Latin America, South Asia, we still have some issues in some parts of the countries where it's very hard to get access to electricity. And this brings us to the problem of energy as a whole, especially electricity as a problem. So what are the main problems? Well, we have insufficient infrastructure to deliver electricity to everybody. There are some countries, as I told you, that continue to have limited access to electricity. The power supply of this electricity is intermittent, which means that sometimes it's very hard to actually produce more electricity if we need it. Our power grids are becoming very old. We, of course, have losses in terms of monetary return because of theft and of this energy. We depend a lot on fossil fuels, as you can saw, and as you saw a moment ago. Well, we are actually bounded to natural disasters. Sometimes the grid goes down because there was an earthquake or anything else. And of course, we have a significant political and regulatory issues that will impact only the electricity, but also the cost of the same. And this brings us to the high costs of energy production, which part is really due to the technology available, but other part is actually because of political and regulatory issues also. And then we have the limit, let's say, one of the biggest problems, which is how we storage this energy and how can we use this energy if we are able to store it. And one of the biggest sources of energy of all times is here. Actually, if you look to the sky during the daylight, you'll see it. It's solar energy. You can have huge amounts of energy values that are right here. It's free. It's easy to get it. The problem with solar energy is that part of this energy does not get to Earth. So it is reflected in atmosphere. It has several struggles with clouds and other types of atmospheric challenges. Some of part is reflected from the Earth either. And more important than that, solar energy, despite it's free and is available in a huge amount of power there, it's an intermittent energy. What that means, it means that it depends on the day, if it's daylight or if it's night, and it depends, as I said, on the season, because if it's raining or if it is cloudy, then the amount of energy that gets to the earth is very, very complex. More important than that, if we want to get a lot of amount of this energy, as you can see in the image below this slide, we need to have these huge solar farms. And these huge solar farms in certain parts of the world is very difficult to actually build them, because you need a large amount of areas to actually build these solar farms. So what can we do, and how microwave engineers can actually help this energy role problem? Well, we can help if we bring these solar panels to space. We can actually deploy the solar panels in space. And if we deploy the solar panels in space, you'll have 24 hours of daylight, because you will have always sun visible light available, and we don't have an atmospheric problem. We are out of the atmosphere, but we need to bring this energy from space back to Earth. And how can we do that? Well, we can do that exactly with wireless power transmission. We can actually build what it's called space-based power satellites, which, as you can see here, these slides are actually from the European Space Agency. You can collect energy out of space, beam that energy to the ground, and then convert it again into our electricity, and actually feed our electricity grid with this amount of energy. And this is not actually science fiction. And there, in the recent years, this is happening since the 80s, since the last century. NASA was one of the first look into this. There was a huge amount of colleagues from Japan actually working on these activities. And more recently, other countries, other continent joined this effort. And you can see some examples in China, Japan, in the United States, in Europe. There is a huge project in Europe now called Solaris. And you can see actually on the left side of this slide, some documents, some texts that were published recently about how can we use this for the impact and for the advance of humanity. So this is really one possibility to bring this energy back to ground. And I will give an example of one of the companies that will join us in IMS this year, which is Emerald, that is actually picking up these concepts and bring it to commercial products. As you can see here, these images actually come from their website. They are publicly available, and you can see some of the links that they are building, some of the solutions they are using far-field wireless power transmission to supply energy in places where you don't have energy or you don't have access to energy. And this is really one good opportunity for doing this. But this is not only a problem on Earth. You can also bring this concept to space exploration. And one of the examples is on the moon. And there are also some space agencies looking to how can we supply energy to the moon base stations or to the moon bases. And the problem is similar on Earth. And I will say it's even worse if we go to space, because we have 15 days of darkness and 15 days of light. So it would be nice also to come up with ideas of how we can actually collect energy from the sun and beam to the places where we really need it. So this is one of the topics that we are going to have in IMS this year. And we have a special session that is going to happen on Tuesday. It's called Microwave-Based Space-Based Solar Power, and is actually as this group of very well-known researchers on this field. So we are going to have Ali Ajimiri from Caltech, we are going to have Naoki Shinohara from Kyoto University, Volker Ziegler from Airbus, Sanjay Vijayendran from ESA, and Paul Jaff from DARPA. So I think it's going to be a huge opportunity for you to know a little bit more about space-based solar power and how can we bring energy from space back to Earth using microwaves signals. But on top of that, I think not only these major projects are very important, major, and we are talking about megawatts, terawatts of energy, but sometimes we need to power very small devices. It would be nice if we can power, for instance, our mobile phone, charge our mobile phone everywhere. So can we bring these long-range wireless power approaches to day-to-day life? Well, we probably can. And this is one of the examples I'm showing in this slide of Xiaomi. Xiaomi is one of the mobile phone manufacturers where they were trying to have a beam of energy that can actually power your mobile phone. And this, of course, goes back to how can we charge, or can we remove the batteries of our gadgets? And we are not only talking about mobile phones, we are talking about mobile phones, smartwatches, we are talking about all these gadgets. And how can we, or why should we do that? Well, first, because batteries so batteries should be recycled and sometimes get to the garbage sometimes. So it will be very nice if we can have a solution that can charge all our gadgets, can give energy to our gadgets without using this type of lithium batteries that we want to remove. So this is also another topic that we are going to address this year at IMS on our featured days on wireless power transmission. And as you can see in this slide, these are some of the companies, Reach, OSIA, PowerCast, that are already doing some of these solutions to remove the batteries, or at least to increase the battery lifetime in all our gadgets. So again, on Tuesday, during lunchtime, we are going to have a very nice panel session on the concept, will long-range wireless power transmission become a reality? And the speakers will be Greg Kushner from Emerald, Volker Ziegler from Airbus, Chris Davlans from Reach, Jennifer Grants from OSIA, Jason Gill from PowerCast, and Dinesh Kitani from Want. So you are all invited to these two very interesting sessions during IMS talking about long-range wireless power transmission. So thank you very much for listening to this part of the long-range wireless power transmission. And now I will invite Professor Jasmine Grossinger from Graz University. Jasmine Grossinger is also an HATCOM Microwave Theory Technology Society member, and she will talk briefly about other very interesting topics on near-field wireless power technologies. Jasmine, please. I will stop.
Thank you so much, Nuno. Thank you so much, Nuno. And as already announced by Nuno, there is another very interesting technology available within the portfolio of wireless power technologies. And one of them is, next to far-field technologies that were presented by Nuno, one of them is near-field wireless power technologies that we already use altogether as consumer with our consumer electronics. And here you can see from the Apple website some gadgets which are already powered up, charged by wireless power transfer in the near field. And wireless power transfer in the near field already provides some standards. So what we use usually in our gadget, like the smartphone or our watch, is the key wireless charging standard provided by the Wireless Power Consortium. It allows you to create power from 5 to 15 watts and is designed usually for these mobile devices. And very often you just have to take a look. You will find it on your device yourself. Of course, and another interesting development that we've seen recently is next to this already established Wireless Power Consortium standard, the key wireless charging, is the activities provided by the NFC forum. NFC is near field communication and is also a thing that you use daily for contactless payment. It is the same technology, magnetic resonant coupling, near field wireless power technologies, but it gives you also the possibility next to charging your device to communicate with your device. Currently, the NFC wireless charging standard provides power up to 1 watt. So it's low power in comparison to key wireless charging and is designed also for personal and wearable devices. And the cool thing about it is it also provides and includes an NFC interface for communication. And very often what you see in your mobile phones here, these are some antennas integrated in a Huawei mobile phone, is seeing these both type of coils that are necessary to establish key wireless charging. Here you see this coil and NFC communication. So you have it already on board of your phone. So going fully to NFC charging is something that is just a step away. And NFC also, as I said, provides you not only this new charging feature, where they plan now to build up the capability of charging, of providing power up to 3 watts. It also gives you the possibility that, you know, your phone can act as a tag, a rider, or as a reader or a writer. So your tag acts as your payment card for contactless payment, or as the reader itself to read out some data. And the card emulation is something that we use for payment. So we have various operation modes coming with NFC. And there is a company that will also be part of one of our events at the Future Directions Day at IMS in Washington, D.C., and that is Renesas Electronics. And they already provide chipsets for NFC charging, which is quite interesting and gives, from the technological point of view, quite some challenges in terms of how I can provide efficiently power, but still communicate. Or can I just provide power and get rid of the communication interface to be more efficient in power transfer? And this is something that we will discuss in our Wireless Power Technologies Bootcamp. And it will be on Monday of IMS, and we will have 2 parts. It's a full half-day event, but I'll give you more information on it in a minute. We have 1 part dealing with near-field wireless power technologies and taking a look at how we power up consumer electronics at short distances. And the other part is on far-field wireless power technologies, how we might possibly can power up consumer electronics in a far distance. So somewhere in the room, and the transmitter, the wireless power transmitter, is installed somewhere here, which is quite challenging. And we will have these 4 speakers, 2 people from academia. It's me and Nuno, speaking about the theoretical background of the technologies. And then on top of this, we will have 2 industry speakers giving you information on the business aspects of these 2 technologies. So for NFC charging, we have Jerne. He is product manager at Renesas Electronics here in Austria, in Graz. And then on the other side, for far-field wireless power technologies, we have from OSSIA the Chief Revenue Officer, Jennifer Krenz. And she will also give an impact, give you a glimpse of how the market looks like and all the market questions that you will have regarding far-field wireless power technologies for consumer electronics. And at the bootcamp, as I said, it will be on Monday, so 17th of June. It will be a half-day workshop, and we have these two 1-hour sessions, one devoted to near field, the other one in far field, and equally distributing talks by academia and industry. And of course, we hope to see you there. And just to give you a glimpse of what you will learn and experience at the bootcamp, is something like this. So this comes with the theory. We have, for example, a transmitter to provide power. It is magnetically resonant coupled, here in this case, for NFC, so at 13.56 megahertz. And we have the receiver that we in this call very often call a transponder, because we come in from the RFID world. And it's also magnetically resonant coupled at 13.56 megahertz. And what you will learn is, how can I design the coil at my mobile phone, for example, together with the chip that is provided by, for example, Infineon, NXP, or Renesas? How can I resonate the coil? How can I design the coil to have resonance at 13.56 megahertz and to establish wireless power transfer? And if you wish, on top of it, enable communication. So what you can do, for example, then is to have a battery-less sensor in your industry setup, and then to power up the sensor with your mobile phone and read out the sensor data. Here I show you a little video where we applied this technology for a company here in the Graz region in the automotive industry, and we read out the sensor data through actually an enclosed metal housing. And here you can see that on top of providing wireless power to the device, we can also communicate it and see that the sensor tag temper status is okay, and there has been no breach in over temperature in this case. Another interesting topic that you will experience at the bootcamp is, so as soon as you have a bit of misalignment between your two devices, the transmitter and the wireless power transfer receiver, you will see a performance loss. So it really depends on these alignments and the coupling of these two coils. And what you can do to, get rid of any performance loss is you just can establish an adaptive matching network steered by artificial intelligence to help you increase the performance again in case you have any misalignment. And here I just show you as a final slide, a little video where you can see two magnetically coupled resonators at 13.56 megahertz. We have here the receiver device, here the transmitter device, and we have automatic misalignment just to test then our matching network and if the AI algorithm is actually performing well. So here you can see now we're starting the movement. We have here our adaptive matching network where leads are actually showing us which capacitor, which varactor in the matching network is switched by the deep neural network that we've trained to do it. Here can you see the changes in the voltage. And what you'll see then, of course, we need a power detector. All these things are quite detailed. I don't think that we go that much into detail at the bootcamp to give you an overall experience. But what you'll see is actually that as soon as you have a misalignment, a new one, the algorithm improves the matching, which shows you it goes again to a lower level, as you can see it here. So this was just a little sneak peek also from my side and from Nuno. And we are very happy to see you then at IMS in Washington, D.C. in June.
Okay, thank you very much.